Hello all. So in the previous lecture we have seen what is internal hashing. So in this lecture we'll see about external hashing. So we'll see external hashing for disk files. Then what do you mean by this extendable hashing, dynamic hashing and linear hashing. So external hashing. So hashing for disk files is called external hashing. So in internal hashing what we have seen is within files we have to find records and all. So for finding those records, we will apply those hash functions. Now external hashing is for disk files. That is whatever that is kept in the secondary memory or the hard disk. We need to retrieve those information. So for that we will be using this external hashing. Okay. So the target address, so to suit the characteristics of this disk storage, the target address space is made of buckets, and each bucket will hold multiple records. Okay, the multiple records will be there in buckets. So we call it as buckets. So the target address space. So where when we apply this target hash function, we will get a value. So that will be bucket. That will be the bucket address. Okay. So we call it as bucket. And each bucket will hold multiple records. So a bucket is either one disk block. It may be a single disk block, or it may be a cluster of contiguous disk blocks. It may be a contiguous disk blocks. It may be a cluster of contiguous disk blocks. That is, it is a consecutive disk blocks. So it may contain 10 disk blocks which are in consecutive memory locations. Okay. So bucket is either one disk block or a cluster of contiguous disk blocks. Then hash function maps a key into a relative bucket number. So here when we apply this hash function, the result will map the key value into a bucket number. It will be a bucket number. So we will get bucket number 0, 1, 2, 3 like that we will get. And in that bucket what we have, it may hold one disk block address, or it can be a cluster of contiguous disk block addresses. Okay. Here we maintain a table in the file header, and this table converts a bucket number into the corresponding disk block address. So this is what is happening here. So we maintain a table with the file header converts a bucket number. So we get a bucket number. The hash function, when we apply, we get a bucket number, and in this table we can convert this bucket number into the corresponding disk block address. So this is external hashing. This is also known as static hashing because buckets is fixed. The number of buckets is fixed. That is why it is known as static hashing. Okay. So external hashing. So this is the bucket numbers. We have 0, 1, 2, 3, etc. These are the different bucket numbers, and we have block addresses. So each bucket number will correspond to a block address. So it may be a single block, or it may be a contiguous blocks. So it will contain a block, and that block will be connected to some other block, and that block will be connected to some other block, like that it may be. So when we apply this hash function, what we get is the bucket number. So if we get 2, by searching this table we get the block address of the disk. By going to that block address we can find the records. So in this block address, in this block there will be n number of records will be stored. So by searching that we can find the appropriate thing. Okay. So here collation problem is less severe. There may not be any collation at all, because we can fit many records in a bucket, because in this bucket we have a bucket address. When we apply the hash function, we will get the bucket number. For example, if we get the bucket number as 2, what we get here is the block address. So this block address is actually this block, and this block can be connected to any number of blocks. So hashing won't be a problem. That means collation won't be a problem here, because we can fit many records inside this bucket. Okay. But still collision can occur. So in order to remove that collision, we have a technique here. What we do is we use a technique like this. Okay. So we use overflow buckets here. Overflow buckets will be used here in order to avoid this collision. Okay. So what we do is we have bucket like this, bucket 0, bucket 1, bucket 2 like that there, and it will be holding different blocks. Okay, each block will be have different blocks, and if a collision occurs, what we have is a record pointer also. We have a pointer, and this is a pointer. This is a linked list actually. The pointers in the linked list. This is record pointer which will include the block address and the relative record position within the block. So it will contain the block number plus the appropriate relative record position. So inside this disk it will be in a particular position. So it will also be stored in this. Okay. So if overflow occurs, so this can be connected like this. So if this bucket is overflow, we will add some other overflow bucket here, and we can add those like this. So bucket 2 has overflow. So it is also connected to this one. So if hash function when applied, it is full. If this bucket is full, it will store in the overflow buckets. Okay. So this way we can work. Okay. So here also, here overflow buckets can also overflow. Then it will be connected to another overflow bucket. So this way we can handle this overflow condition. So this is handled using the chaining. So this is actually the chaining method we have already discussed in internal hashing technique. Okay. So this is static hashing. As I have mentioned, this is called static action because the number of buckets is fixed. This bucket number is fixed here. So if we see, we have m number of buckets. This bucket number is fixed. So that is why it is known as static hashing. Now we will see another type of hashing where hashing that allow dynamic file expansion. Here we can this allows dynamic file expansion. Whenever it is full or overflow, we can expand it dynamically. So a drawback of static action is that hash address space is fixed. That is, the number of buckets is fixed there. So if we want to expand or if we want to shrink the file, it is not possible in static hashing. So for that we use this dynamic file expansion techniques. So we have three methods here: extendable hashing, dynamic hashing, and linear hashing. So we will see each one separately. First one is extendable hashing. So in extendable hashing, what we do is we have a directory. We call it as a directory, and that directory will contain an array of 2 raised to d bucket addresses. 2 raised to d addresses, bucket addresses will be there in that directory. So it is a directory. What we do in extendable hashing is we have a type of directory. Actually, this directory is an array of 2 raised to d bucket addresses, and d is called the global depth of the directory. We call it as the global depth of the directory. So it is an integer value. So it is an integer value. So it is an integer value corresponding to the first d bits of the hash value is used as an index to the array. We will see an example, then you will understand what is written here. Then address in that entry determines a bucket in which the corresponding records are stored. So it does not have to be distinct bucket for each of the 2 raised to d locations. So several, we will see an example, then you will understand. So this is the example for this. So we have a directory. In extendable hashing, we have a directory. We have a directory with 2 raised to d entries. 2 raised to d entries where d is the global depth. So here global depth d we have taken it as 3. So 2 raised to 3 means there will be 8 entries in this. 8 entries will be there. Okay. So there will be 8 entries, and 8 entries, for each entry it is identified with higher order bits, that is 000, this is 001, like that up to 111, that is 7, up to 7 it will be there. Now using the higher order bits we can identify the local data file buckets. So in this we have the entry to this local buckets. Okay. So here d is called the global depth of the directory, and higher order bits of the hash value will be the index to that array. Then address in that entry determines the bucket in which the corresponding records are stored. So 000 means it is stored in this local bucket. So buckets for records whose hash value. So whenever hash function is applied, when we get a value 000, then it will be there in this bucket. All the records will be there in this bucket. If it is 001, it will be there in this bucket. Okay, like that. So does not have to be distinct bucket for each of the 2 raised to d directory locations. So if you see that, even though we have 7 entries in the directory, 8 entries in the directory, there we do not have 8 data file buckets. We have only 1, 2, 3, 4, 5, 6. So there need not be distinct entries. So if you see this, we can see that 010 and 011 is actually mapped to the same bucket. Similarly, 100 and 100 is mapped to the same bucket. So that is what we have written here. Does not have to be distinct bucket for each of the 2 raised to d directory locations. Then several directory locations with the same first d dash bits for their hash values may contain the same bucket. So that is what we see here. So if we see here the 3 bits 001 and this is 001. So the first 2 bits it is 00, sorry it is not there. We will take this one 010 and 011. The first 2 bits are 01. So 01, the 01, all these two are mapped to this this data file. That is why we have written here bucket for records whose hash value start with 01 is stored in this bucket. So we can map like that. And similarly, we are mapping these two, which are starting with 10. So 10, 100 and 101. So both these addresses are mapped to the same bucket. That is why we are written here buckets for records whose hash values start with 10 are mapped here. Okay. So several directory locations with the same first d dash bits for their hash values may contain the same bucket. So we call this d dash as a local depth stored with each bucket, and this specifies the number of bits on which the bucket contents are based. So here d dash is 2. Okay, we will take only the first 2 bits. If we see here d dash equal to 3, that is we will take the first 3 bits. Here also d dash is 3, so we have to take the first 3 bits. Here d dash is 2, we have to take only 2 bits. So we have a local depth for each bucket. This is also specified. Okay, so this way we can use this thing. So why this is used is, why we use this d is, we have already mentioned that we can expand or shrink. If we want to expand, it is possible. If we want to shrink, for example, in this d dash equal to 2, now if this has been full, this bucket is full now, what happened is we cannot store anything in this. So this bucket is full. So what we have to do is we have to split into 2. So what we can do, so we will change the depth d dash equal to 2 to d dash equal to 3, and we will map 010 to one bucket, and another we will add one more bucket as 011. So like that we can expand. So if this bucket becomes full, we can add, we can split it into 2, or we can add it into or split into 2. We call it a splitting. Okay, we will split into 2. So it will be changed to 01. So here it is 01. We have mapped 010 and 011 to here, this one. So starting with 0. So when we want to split, what we have to do is 010 will be mapped to one bucket, and another 011 will be mapped to another bucket. Okay. Similarly, this we can split. Also, if we want, we can shrink also. So if all the elements in this element in this is empty, only one element is there. Here also in this bucket also one element is there. So we can combine this. So what we have to do, we have to change d dash value to local depth to 2, and we can add those records into this bucket. Like that we can shrink and expand when we use this dynamic hashing. Okay, so that is the advantage of this. So as the file grows, so advantages for this extendable hashing is performance of the file does not degrade as the file grows. So even the file grows or the number of records increases, performance does not degrade at all. So we can extend it. That is why it is known as extendable hashing. So no space is allocated in extendable hashing for future growth. There is no overflow buckets at all. We can simply add it dynamically. Okay. Splitting causes only minor reorganization. So when we split it into two buckets, only a minor reorganization is needed. But it is more expensive is when the directory has to be doubled. So this is expensive when the directory has to be doubled. But it is okay. But there is a disadvantage with this thing. The main disadvantage is directory must be searched before accessing the buckets themselves. So it results in two block access, because if you see this, we have a directory and also a data block. So this directory is also in the disk and this is also in the disk. So we need two disk access. First we have to search this directory, then we have to find the appropriate data file. So both will require two disk access. So that is the disadvantage. So two disk access is needed. Directory must be searched before accessing the buckets themselves, resulting in two block accesses. So we need to access the block twice, or the disk need to be accessed twice. Then the second type of hashing, dynamic hashing, is we call it as dynamic hashing. So here addresses of the buckets are either the n higher order bits or n minus 1 higher order bits. So it depends on the number of keys on the buckets or on the respective buckets. So storage of records in buckets is somewhat similar to that extendable hashing. It is somewhat similar to that extendable hashing. Difference is it is an organization of directory. So there is no directory like structure here. We do not have a directory like the extendable hashing. So we maintain a tree structure directory with two types of nodes. One is the internal node that have two pointers, the left pointer corresponding to the 0 bit in the hashed address and the right pointer corresponding to the 1 bit. Leaf nodes where these hold the pointer in the actual bucket with records. You will see an example, then you will understand. So this is the organization of dynamic hashing. So it is like a tree structure. There is no directory here. There is no directory as in the extendable hashing. There is no directory here. This directory is a tree structure. So we have 0 and 1. That is what is written here, 0 and 1. So internal nodes will have two pointers. The left pointer corresponding to the 0 bit in the hash address and the right pointer corresponding to the 1 bit. So that is what is here. So 0 and a 1. So here also it will have a 0 and a 1. So here also it will have a 0 and 1. So all the internal directory nodes will have 0 and 1, and the leaf node will correspond to the particular address. That is what written here. Leaf nodes will hold a pointer to the actual bucket with records. So leaf will have the actual address of the bucket. So leaf will be holding all the actual bucket address. So this is actually an example for 4 buckets. So we have 4 buckets with 0, 0, 0, 0, 1, then 1, 1, 0 and 1, 1 is there. Okay, the same thing in the previous case we have seen the same thing. So if we want to have access a particular bucket, it is like this: 0, 0, 0, we can access this one. Then 0, 0, 1, we can access this bucket. Then 0, 1, we can access this bucket. Then 1, 0, we can access this bucket. And similarly, there is 1, 1, 0, we can access this bucket. Similarly, 1, 1, 1, we can access this bucket. So it should be read like this. Okay, that's why there is a directory structure like this. Okay, there is no directory as in the previous case. We have a directory structure like this. So that is the difference. The organization of the directory is different. So we can access. This is the same example we have seen in the extendable hashing. So that is what we have written here. So we have internal nodes and leaf nodes. Then the third type of hashing is dynamic hashing, is linear hashing. So here what we have is it is to allow a hash file to expand and shrink its number of buckets dynamically without needing a directory. So in the previous two cases we need directory. So here in linear hashing we can expand and shrink its number of buckets dynamically without a directory itself. So that's the advantage. So file starts with m buckets numbered from 0 to m minus 1, And we use the mode hash functions like h of k equal to k mod m. We have already seen this hash function. So this is the simplest hash function. So we call this as initial hash function. We have an initial hash function. We call this as initial hash function and it is denoted as hi. Let it be hi. Now, when a collision leads to an overflow record in any file bucket, the first bucket in the file, that is bucket 0, is split into two buckets, the original bucket 0 and a new bucket m at the end of the file. So we have file buckets from 0 to m minus 1. Now if a collision occurs, collision means if an overflow record occurs, what you have to do is we'll take the first bucket in the file, bucket 0, and it is split into two buckets, the original bucket 0 and a new bucket m at the end of the file. Then records originally in bucket 0 are distributed between these two buckets based on a new hashing function h of k equal to k mod 2m. So this is what we do in linear hashing. So here what we have is we will start with an initial hash function k mod m, and when the buckets get full, so well a collision will occur. So we need to have overflow record. So then what we will do is we will take bucket 0, we will split into two buckets. Okay, bucket 0 and a new bucket m at the end of the file. Now we have to apply some function, hash function. So here we will change that hash function to k mod 2m. Instead of k mod m, this hash function is k mod 2m. So when we apply this k mod 2m hash function, it will be evenly split, or it will be the records will be distributed between these two split buckets. Okay. So that is the use of this linear hashing. So this can also dynamically expand. So there is no directory here. So first we will apply some more initial hash function hi, and if some collision occurs, we will split a bucket into two by applying this hash function. Okay, another hash function. This is k mod 2m. This is k mod m. So in this way we can dynamically expand it. So this is known as linear hashing. So this is a reference. Thank you.